everyone, welcome back to the lecture series of Molecular Symmetry under Group Theory. In the last session, we had a discussion on symmetry, symmetry elements and symmetry operations, and their classification also. Let us have a brief review of what we have learned in the previous session. All the symmetry elements of a molecule have one point in common, right? That is, it is the center of gravity. It should not be changed upon carrying out any operation. There are only 5 basic operations which leaves this central point or the center of gravity invariant or unmoved or unchanged. These are identity operation, inversion, proper axis of rotation, reflection and improper axis of rotation. Out of these 5, 3 of them were discussed in detail, and that is what? Identity operation, inversion and proper axis of rotation. Now, let us continue with the fourth one, that is reflection. To begin with, I would like to have a discussion on the symmetry planes of a cube. A cube has 9 planes of symmetries. 3 rectangular planes of symmetry dividing it to 2 halves, as you can see in the figure. It is in the first row. And 6 diagonal planes of symmetry that divides the cube into prisms. Now, one may ask, in total how many elements of symmetry does a cube have? Well, as can be seen, a total of 23 elements of symmetries exist for a cube. They are one center of symmetry and a total of 9 planes of symmetries, that is 3 rectangular planes and 6 diagonal planes of symmetries, and also 13 axes of symmetries like 6 dyad axes, 4 triad axes and 3 tetrad axes respectively. Altogether 23 elements of symmetries, right? Now, another interesting fact is that your hand also holds symmetry. By what means? Did you notice when we show our left hand to the mirror will show right hand. That is, right and left hands are identical by reflection through a mirror plane. Do you ever notice the babies looking mirror and their expression by seeing they are alike? Look at the hand of this baby and its mirror image. It is the mirror plane symmetry. Coming to the molecular symmetry, a plane of symmetry is an imaginary plane that bisects a molecule into 2 halves that are mirror images of each other. It is otherwise called mirror plane, represented by sigma. For any planar molecule, the molecular plane itself is a plane of symmetry. The plane of symmetry can be of 3 types, that is vertical, horizontal and dihedral. The vertical plane of symmetry contains the principal axis of the molecule, that is symbolized as a sigma v, while the horizontal plane of symmetry is the one which is perpendicular to the principal axis, which is represented as sigma h. And now, dihedral planes of symmetry. The dihedral planes of symmetry contains the principal axis and also that bisects the angle between the 2 similar C2s adjacent to it, which is denoted as sigma d. Now, let us exemplify each. Water is a molecule containing sigma v. Let us look in detail. Water molecule has 2 symmetry planes which are perpendicular to each other. One is the molecular plane passing through the HOH denoted as sigma v dash, and another is passing through the oxygen and reflects the 2 hydrogens in both sides, that is sigma v. Both contain principal axis and hence they are vertical planes of symmetries. Since they are 2 in numbers, to distinguish them, one is labelled with a prime or dash. Hence, they are represented as a sigma v and a sigma v dash, or otherwise sigma v and a sigma v prime. One plane contains the molecule and one plane bisects the molecule. Both are sigma v's. since they contain the principal axis. Another molecule that contains sigma V is ammonia. Ammonia molecule has 3 vertical planes of symmetries, each of which contain principal axis. The 3 mirror planes designated as sigma V dash and sigma V double dash run through the principal axis in the ammonia. In these figures, the central point indicates the principal axis. Each sigma V passes through the nitrogen atom and one of the hydrogen atoms and also bisecting the angle between the other 2 nitrogen and the hydrogen bonds, NH bonds. The molecule CH3Cl also has 3 sigma V's, each of which passes through the central carbon and chlorine along with one of the hydrogens. One is represented in the figure and likewise 2 more sigma V's can be drawn. BF3 molecule have 3 vertical planes of symmetry, that is 3 sigma V's, each of which passing through the principal axis, or it contains the principal axis. The central point designates the principal axis. Each of the sigma V passes through the boron atom and a fluorine atom and also it bisects the angle between the 2 BF bonds. As you can see in the first figure, the molecule also bears a horizontal plane of symmetry sigma H, which is perpendicular to the C3 axis and to the sigma V's also. From the figure, it is evident that sigma H is the molecular plane itself. Another example for a molecule containing the sigma V is HCl. HCl is a linear molecule and has an infinite number of vertical mirror planes, all of them containing C infinity axis. One is depicted in the first figure. Likewise, infinite numbers of sigma V planes can be possible, as in the second figure. Here you can see nitrogen molecule N2. Like HCl, it is a linear one, moreover it is symmetrical too, since it contains similar atoms on the both sides, right. The symmetrical linear molecules like N2, O2, H2 etc. have an infinite number of vertical mirror planes that containing C infinity axis. One is depicted in the first figure. Likewise, infinite number of sigma V planes can be possible as in the second figure. These type of molecules possess horizontal mirror plane sigma H perpendicular to the C infinity axis as in the third figure. It is important to note that the HCl molecule do not possess sigma H since its both sides are not similar. Now, you consider the alene molecule. Alene molecule is what? CH2 double bond C double bond CH2. The alene is a molecule in which the 2 CH2 groups lie in a plane perpendicular to each other. You can see here the 2 planes are perpendicular to each other. It resembles the CH4 molecule, which is a tetrahedral one. The only change is in the carbon. The carbon in the central portion of the CH4 is replaced by C double bond C in alene. Like in CH4, the alene has 3 perpendicular C2s as can be seen, and also 2 sigma Ds, that is 2 dihedral planes. Let us recall the condition for a sigma D. The dihedral planes of symmetry is the plane that contain principal axis and also bisects the angle between the 2 similar C2 axes adjacent to it. Is it true here? Here there are 3 C2s, hence the principal axis is C2 itself. You can see clearly in the first figure that the plane contains one C2, that is plane contain principal axis, and the other 2 C2s are perpendicular to each other and the plane bisects the angle between them. In this figure, you can clearly see how the plane bisects the 2 adjacent perpendicular C2s. Besides, it contains principal axis also. Hence, the plane is a dihedral one. You can see one more dihedral plane in the next figure. Therefore, alene molecule has a 2 sigma Ds. In the case of symmetrical tetrahedral molecule like a CH4, it has 6 dihedral planes of symmetry, each one passing through the carbon atom and 2 of the hydrogens. This is understood well if we place the methane molecule in a cube so that the carbon atom is at the center and the hydrogen atoms are at 4 vertices as we discussed earlier. The 4 hydrogens are labelled here as HA, HB, HC and HD respectively. The plane in the second figure contains the principal axis and bisects the angle between the adjacent perpendicular C2s. Hence, it is a dihedral plane. I already mentioned that there are 6 sigma Ds for methane molecule. They are C, HAHB, HAHC, HAHD, HBHC, HBHD and CHCHD respectively. That is, the possible combinations are the hydrogens labelled with AB, AC, AD, then BC, BD and lastly CD. 2 of them are depicted here. In figure, you can see the planes CHBHC and then CHBHD respectively. Those planes bisects the other 2 hydrogens, right? I am concluding the discussion of planes of symmetry with one last example, that is benzene. We already know that the principal axis of the benzene is C6. From the figure 1, it can be understood that the molecular plane of the benzene is a sigma h as it lies perpendicular to the C6, that is principal axis. I want to make it little more clear. See the figure 2. Here the C6 is represented as a dot, which indicates the axis is directing towards you from the screen. The molecular plane is perpendicular to C6. Hence, the molecular plane is sigma h. Also, the benzene have 3 sigma Ds and 3 sigma Vs, as you can see in the picture, right? How they are possible? Let us look. Both sets of planes contain C6, that is principal axis. The 3 planes in the figure 3 bisecting the opposite edges of the hexagon. They are dihedral symmetry planes. Now, you can see how the dihedral planes of symmetry bisect the angle between the adjacent C2s. The other set of planes we are discussing is passing through the opposite corners depicted in the figure 4, right? They are vertical symmetry planes. Hence, for benzene there are 7 symmetry planes altogether, that is 1 sigma h, 3 sigma Ds and 3 sigma Vs. Now, before going to the 5th symmetry operation, that is improper rotation of axis, let me introduce the nomenclature system for representing symmetry operations and elements. There are 2 distinct methods of nomenclature. One is Hermann-Mauguin nomenclature and the other one is Schoenflies nomenclature. The Hermann-Mauguin system of nomenclature is named after the German crystallographer Carl Hermann, who introduced it in 1928, and the French mineralogist Charles Victor Mauguin, who modified that in 1931. The Hermann-Mauguin system of nomenclature is typically used to describe crystals and crystallographic symmetry. The Schoenflies notation is named after the German mathematician Arthur Maurice Schoenflies, and this convention is primarily used to describe symmetry in discrete molecules in optical spectroscopy and in quantum mechanics. So, when we deal with crystals, we use Hermann-Mauguin notations, and when we handle molecules, then we use Schoenflies symbols. Is it clear to you? Now, let us look the difference in notations according to the 2 methods. The identity operation is symbolized as a E, that is capital letter E in a Schoenflies notation, whereas it is represented as 1 in Hermann-Mauguin notation. and mirror plane is represented as a sigma in Schoenflies, while it is m for mirror plane. Now, the axis of rotation is represented as a Cn in Schoenflies method, and while it is n in Hermann-Mauguin notation. The center of inversion is denoted as I in a Schoenflies symbol system, whereas it is 1 bar in Hermann-Mauguin notation. And one thing we have to remember is that the improper rotation of axis is otherwise called rotor reflection axis in a Schoenflies symbol system, and it is represented as a Sn, while the same improper rotation axis is represented as a roto inversion axis, and which is symbolized as a n bar in Hermann-Mauguin method. Now, let us discuss the fifth element of symmetry, that is improper rotation axis, and its operation improper rotation, or it is otherwise called rotor reflection in Schoenflies method and roto inversion in Hermann-Mauguin method, as we said earlier, and the symbol is a Sn, right. In the Hermann-Mauguin system of nomenclature, the improper rotations are sometimes called roto inversions, as we said earlier. In the Schoenflies scheme, the improper rotations are roto reflection axis, because there are a rotation followed by a reflection that is perpendicular to the rotation axis. If a rotation of a molecule about an axis through a certain angle followed by reflection in a plane perpendicular to the axis yields an equivalent configuration, then the axis is called an improper rotation axis or roto reflection axis. That means an improper rotation is performed by rotating the molecule by 360 divided by n degrees followed by reflection through the plane perpendicular to the rotation axis. If the resulting configuration is indistinguishable from the original, we say there exists an n-fold improper rotation axis or Sn axis in the molecule. That is, if a rotation and a reflection is combined to form a single hybrid operation, the resulting operation is called roto reflection. The combination of rotation and reflection always gives the same result regardless of the order in which they are performed. Inversion is equivalent to the reflection through a point. Therefore, it is possible to combine an inversion with a rotation axis to produce roto inversion axis, okay, in a manner similar to the formation of roto reflection axis. Hence, the improper rotations are sometimes called roto inversions. Rotation inversion axis is a symmetry element which has a compound operation of a proper rotation and an inversion. A crystal structure is said to have possess a rotation inversion axis or a roto inversion axis if it is brought into a self coincidence by the rotation followed by the inversion about the lattice point through which the rotation axis passes. For example, see the picture here. 180 degree rotation and then reflection gives the same result as 0 or a 360 degree rotation after the inversion. That is, the green ball is first rotated through 180 degree and then it is reflected, which gives the same effect when it is rotated through 0 or a 360 degree and then inverted. Roto reflection and roto inversion are same if they differ in an angle of rotation by 180 degree and the point of inversion is in the plane of a reflection, right. An improper rotation of an object thus produces a rotation of its mirror image. The axis is called the rotation in reflection axis or a roto reflection axis. Now, let us look the conditions for a Sn axis. If a molecule possesses Cn and sigma h as independent symmetry operations, then definitely there exists an Sn. For example, the molecule BF3. BF3 molecule has C3 axis and a sigma H also, which confirms the presence of a S3 axis. Likewise, the eclipsed ethane has a C3 axis through the two carbons, that is C1 and C2, and a sigma H perpendicular to the bond axis at its middle. Since it contains C3 and a sigma H, certainly there is an S3 axis collinear with the C3. If both Cn and a sigma H exist, then Sn must exist. However, Sn may exist even when neither Cn nor sigma H exist independently. Molecules having Sn without the presence of required Cn and a sigma H is CH4. Neither CH4 or sigma H is a symmetry operation in the case of this methane molecule, but it has an improper rotation axis S4. CH4 is a regular tetrahedral molecule. It has 3 C2s, each one perpendicular to the faces of the cube containing the tetrahedron, right? These 3 C2s are simultaneously S4 too. Since 90-degree rotation about any of the above axis followed by reflection about the plane perpendicular to it produces an equivalent configuration. Let us perform C4 and a reflection on methane molecule. In figure 1, see how the H1 and H2 changes after C4, that is 90-degree rotation in anti-clockwise direction. See how it changes. H1 goes to the next position and H2 goes to its next position. Likewise, H3 goes to the next position and H4 also goes to the next position, right? Now, the molecule resembles the figure 2. When a reflection in a plane perpendicular to the axis as seen in the figure second one occurs, then it will bring the hydrogens on the top of the cube to the lower part, and those on the lower part will come to the upper portion of the cube as seen in the third figure. Now, look at the first and the third figure, both are identical, right? If the hydrogens were not labeled, one cannot identify which one is original. Hence, methane has S4 axis of symmetry, though it does not contain a C4 and a sigma H. Similarly, 2 more S4 axes are possible which are collinear with the C2s. The combination of rotation and a reflection always gives the same result regardless of the order in which they are performed, that is, no matter which is performed first. Now, let us consider staggered ethane. There is a C3 axis through the carbon-carbon bond, and this C3 axis is an S6 too. It should be noted that here also there is neither a C6 nor a sigma H as independent symmetry elements. So far, we have looked about these various symmetry elements and operations. Now, I would like to draw your attention to the molecular symmetry of water and as well as ammonia. The water molecule possesses 3 symmetry operations in addition to identity. You know already that water has a C2 axis along the Z direction. That is, 180-degree rotation in anti-clockwise manner will bring indistinguishable configuration. And as we discussed earlier, there are 2 sigma V's also, that is, in XZ plane, that is the molecular plane shown in red color, and the other is in YZ plane, which is blue in color. These 4 operations are grouped and named as a C2V point group. C2V point group contain 4 elements, that is E, C2, sigma V XZ and sigma V YZ. Coming to ammonia, it contains identity and 2 C3s and also 3 sigma V's in its point group, that is altogether 6 elements of symmetries. In ammonia, which is a pyramidal molecule, you can see C3 axis, that means a 120-degree rotation about the axis gives indistinguishable orientation. We can observe symmetry after a rotation of a 120 degree, 240 degree and a 360 degree respectively. The 360 degree is otherwise equivalent to 0 degree, right? If the first counterclockwise rotation is 120 degree, that is represented as a C3, then second counterclockwise rotation equivalent to 240 degree is designated as a C3 square, and the third counterclockwise rotation, that is equivalent to 360 degree, is symbolized as a C3 cube. Then C3 cube or a 360 degree rotation is a do nothing operation, right? So, there are two C3 symmetry axes possible. One is C3 and the other is C3 square. C3 cube we do not count as it is identity, right? So, there are two C3s present. Ammonia also contains three vertical planes of symmetry, each of which contain the principal axis. The three mirror planes designated as a sigma V dash and a sigma V double dash run through the principal axis in the ammonia. The central point indicates the principal axis, and each sigma V passes through the nitrogen atom and one of the hydrogen atoms and also bisecting the angle between the other two NH bonds. Hence, the total 6 operations possible for ammonia are E, 2 types of C3s and 3 types of sigma V's, which are grouped together and named as a C3V point group. What is meant by this point group? What is its importance? Let us make the point little more clear. Point groups are consistent combinations of rotations and inversions that can occur in crystals. Apart from the different symmetry elements, different combinations of basic symmetry elements are also possible. They give rise to different symmetry points in the crystals. The combination of symmetry elements at a point is called a point group. A group of geometric entities that keeps at least one point fixed. Hence, the name point group. The point groups are a collection of symmetry operations or otherwise symmetry elements. The number of distinct groups is again finite. There are now 32 point groups or crystal classes possible. When combined with a 14 Bravais lattice, this results in 230 distinct space groups. That means, the combination of non-symmetry operations with the non-translational lattices yield 230 space group types. Every crystalline material has one of these 230 structures. Difference between the point group and the space group is that point groups describe the symmetry of isolated objects, whereas space groups describe the symmetry of infinitely repeating space filling objects. The 32 crystal classes or point groups represent the 32 possible combinations of symmetry operations. Their different combinations result in the formation of 7 crystal systems. You already know about 7 crystal systems, right? These 7 crystal systems are made up by the different combinations of 32 point groups or crystal classes. And the 7 crystal systems include triclinic, monoclinic, orthorhombic, tetragonal, trigonal, hexagonal and cubic. Let us conclude. By this session, I think you are now familiarized with the possible symmetry elements and symmetry operations. And also, we just had a look at the point groups of water and ammonia and the purpose of knowing the symmetry point groups. We will discuss about this in detail in the coming sessions. We will discuss various combinations of symmetry operations also in next session. Let us wind up for today. Thank you.